This is section 5.5a in college algebra, exponential functions and investing. So this one is sticking pretty tight to the whole investment issue, and 5.6 we'll get into loan repayments and annuities and things, but really all we're doing is taking formulas, plugging the information in, and using exponents and logarithms to get your answer. So we're going to be talking about, not in detail, what compound interest is, but we're going to use compound interest in order to solve what we're doing here. So for example, in section 5.4, which is the one that we just really briefly went over, it says that if we have a set of data and we have an initial value A and a constant percent change for equally spaced inputs x, the data can be modeled by the exponential function. And all that's a lot of words for a formula that looks like this. And what we're going to do is we're going to learn how to basically just use this formula. For example, if we invest $1,000, that is my A. That's my initial investment. Okay? And let's say it earns 6% interest. That's my R. And the future at the end of, or the value at the end of T years, and that will be my X right there. And in fact, in this particular formula, it will be a T. Okay? So we've pretty much been given our A, our R, and our T, so that we can find how much money we have at a certain number of years, given this interest rate, given this initial investment of $1,000. So really not too terrible, and we're just going to keep using that particular formula. I'm going to go ahead and erase all this. I'm going to rewrite it here, and we'll look at example 1. So y equals a1 plus r at a certain amount of time t. Okay, so to numerically and graphically view how $1,000 grows at 6% interest compounded annually, do the formula, or do the following. For example 1, construct a table, and they've got a table there on the left, and they're using 0, 1, 2, 3, 4, 5 in order for you to have your t value. And then B says graph that, which you can use your graphing calculator, put in your number of years for your x value, your future value for your y value, and it will give you the graph there, figure 5.42. And then it says graph the function, which is 5.3a, basically connecting the dots. And D, they ask a question, is there another graph that more accurately represents the amount? And the only reason you would use the graph B is because it's compounded annually, so you're going to use this piecewise function in order to get a more accurate idea of what's going on, because you're only going to be able to take the money out at year 1, year 2, year 3, year 4, year 5, or it's only going to grow during those years. And the graph on the left is a continuous graph that makes it look like at the end of 2.5 years you'll have a certain amount of money, and you won't, because it's done annually, so it's only given to you year 1, 2, 3, 4, and 5. So that's why the graph on the right is more accurate there. So all that being said, if you look at the table 5.17, how did they get the y value? Well, they got the y value using this formula and plugging 1,000 in for A, 6% in here, and the number of years here, and that gave them the y. So it's just pretty simple algebra that you did in order to get the future values there. So if you look at the future value of an investment with annual compounding in the middle of page 376, it gives you this formula, which is pretty much exactly this formula here. Your rate, your time, your P is your principal, your initial investment. S represents the future value at the end of this many years. Okay? So what if we compound our interest more often than annually? Okay, this is based on doing it annually. If we do, we have a different formula that we use. It's, well, basically the same formula with just, okay, let me get the, with just a little bit of a glitch here. And we're going to make that into a fraction is all. And I'll put a K there. And what this K represents is how many times we're going to compound the interest. So for example, if this were compounded semi-annually or twice a year, my K here and my K here would end up being a 2. Okay, that's pretty much what we've got there. Let's say that we're doing a compound every month. Well, that K would be 12. So it's just how many times it's compounding per year. So it's every month, it would be a 12. If it was quarterly, that means 4 times a year. So that's how many times it would be compounded. So just so you understand that K is how many times it's compounded. So for example, example 2, find the future value of $10,000 placed in an account earning 8% per year for 10 years if the interest is compounded annually, daily, and then they have another question there. So let's go ahead and get our formula there, which is S equals P 1 plus R over K, K, T. Number of times compounded times time. Okay, that being the case, let's put our numbers in there. We just put $10,000 in there. It's at 8% interest. It's compounded for A annually, so we just put a 1 there. And then our K is 1, and our time period is over the period of 10 years. Okay, and that gives me 21,589.25 at the end of 10 years. It more than doubled. Yeah, those are the old days where you actually got percents or percentage that was high. Okay, so let's look at the next one. It says B, what if it's compounded daily? Well, now we're going to have 10,000, 1 plus 0.08. And how many times is it compounded per year? 365. 365 days. So 365 times 10. And that gives us okay, so not a ton of difference on compounded daily compared to compounded annually. But then for C, they just want you to take the difference of that to find out how much more you're going to be compounding daily. And then the rest of this talks about how to enter the information into your graphing calculator in order to get the information. They just give you step-by-step instructions on how to do that, as well as how to use an Excel spreadsheet to do that. The next part of this lesson has to do with compounding continuously. So, the future investment would look like this formula. Okay, and this is actually the letter E, where that 2.718 yada 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 comes from. It comes from this formula, this investment formula. So anyway, I'm not going to go into detail about where it came from, but that's really where it came from. So pages 378, 379, top of, give you how they developed the formula, how they developed the value of E, etc. I'm not going to go over that. If you want to read through that for casual reading, go ahead and do that. But I'm going to look at this particular formula, the future value of an investment with continuous compounding. So, example 3, what is the future value of 26, let me get my pen here, 2650 invested for 8 years at 12%. Okay, so I guess I don't need that here. I'm going to have an E. My interest rate is 12%. And how long is that? For 8 years. Okay, going to figure that out. Multiply those two together. Take the E value using this button on your calculator. Multiply that by 2650. And you should get $69.21. Okay, so that's pretty much it there. How much interest will be earned on this investment? All right, so all you're going to do is take the amount of money you received minus the amount you invested, and that will give you how much money you made in interest. Okay, so for example number 4, I'm not going to go into a lot of detail here, but they're comparing A, the future value of an investment compounded annually, and that compounded continuously. So what you've got is you've got your annual, you're investing $1,000, 1 plus 8%, 0.08, to the T, and the other one for continuously is going to be E to the 0.08 T. Okay, you can do those on an Excel spreadsheet, you can do those on your calculator, but really what they're doing is just asking you to compare the two. And when you compare the two for one of those, you're going to get your compounding continuously. You're going to make $55.43 more than compounding annually yields. Okay, so this one is going to give you a little bit more money, $55.43 more than this one is when you plug the numbers in. Okay, so that's example 4, bringing us up to present value of an investment, which uses the formula. I think we'll probably end up using this one more. Okay, the other option is to put this in the denominator place because of the negative there. Okay, use either one, doesn't really matter. And so we sometimes need to know the lump sum P, okay, that will give an amount S in the future. So for example, if you're saying, all right, how much money do I need to put in the bank at 10% in order to make $15,000 in 7 years? Okay, that's example 5. What lump sum must be invested, which is your P, because remember, whenever we're using P, that's always been the principal, okay, or how much we invested, and that's what we're looking for there. So, how much do we put in at 10% so that it's worth $17,000 or $15,000 in 7 years? We're going to use this formula. This is how much we want to have. And 1 plus, we put our interest rate in there, which in this case will be 5%. And let me show you where that 5% came from, because the instructions say 10%, don't they? For the investment to grow $15,000 in 7 years. Okay, and we're going to put a 14 there, and I'll explain where that comes from. All right, so first of all, where in the world did I get 0.05 or 5% when I was talking about 10%? All right, so one of the things that we need to look at is this I value. I equals the interest rate over the number of times it's compounded, okay, per year. So in this case, the interest rate is 10%, but it's done twice a year, so that is 5. So that's where the 5% came from. I is equal to RK, or R over K. Make sure that you remember that. Also, where did this 14 come from? Because we're talking about a period of 7 years. So this is where the 14 came from. This letter right here, which is an N, it looks more like an R, that's an N. N stands for the number of compounding periods. Okay, number of compounding periods. Okay, so this is over a course of 7 years, but it says that it's compounded semi-annually or twice a year. So it is being added to your account 14 times during 7 years. So that is where the 14 came from. It's not a T. It does not represent a time period. It represents how many time periods there are that interest is compounded. So now that you have this formula, you can go ahead and get your amount that you need to invest at 10% over 7 years in order to get $15,000. Okay, so that is it for this section. Example 6 talks about mutual fund growth, which follows the exact same examples that we did in 5.4, or at least discussed, as far as using your graphing calculator, putting in the table 5.19, and getting an exponential function out of there in order to use. So really that is exactly like 5.4.